Students, today we are going to see some numericals based on nuclear physics. Dear students, I am not giving any options for the MCQ. If this MCQ, they can ask either in the form of the fill in the blank, or they can ask in the form of true or false. So n number of ways can be constructed by the university. So since you should be thorough with the topic. So my aim is whatever I gave you in the board, that can be the answer. Rest things you need to do by yourself. So in the beginning, in order to study nuclear physics, you should be thorough with the atom structure. We know that. Nucleus is surrounded by the electrons, and the electron is moving, continuously moving. And in the nucleus, there are protons as well as neutrons. So nucleon, that is protons and neutrons, are present inside the nucleus. We all know that. Inside the nucleus, what are present? Protons and neutrons. And the combined word for these two is given as nucleons. Nucleons means protons and the neutrons. Now, if we are interested in calculating the mass of the nucleus, we know that in nucleus there are nucleons. Nucleons means there are protons as well as neutrons. Means what we expect, the total mass will be equal to mass of proton and mass of neutron. But that is not the case. The expected mass of nucleus is sum of the masses of the constituent nucleons. Nucleons means here protons and neutrons. But the actual mass of the nucleus is always less than the expected mass. It's very important. The word less than. They can construct the question like the actual mass of the nucleus is equal to the expected mass, or the actual mass of the nucleus is always greater than the expected mass, like that, or none of the above. So correct answer is always the actual mass of the nucleus, that is in the nucleus what are present, neutrons as well as protons are present, and it is always less than the expected mass. As I mentioned, the expected mass and the actual mass of the nucleus is always, there is a difference. So this difference in the total mass of the nucleons present in the nucleus and the actual mass is called as mass defect. If we will take the difference of the two masses, one is the actual mass and second is the expected mass, and when we will do the difference means minus जब हम करेंगे, so that is called as mass defect. It is denoted by del m, and the formula is given as del m is equal to z times mp plus a minus z times mn minus capital M. Capital M is the actual mass of the nucleus. MP and Mn are the masses of proton and neutron respectively. So based on this, they can ask the numerical, and they will ask you to calculate 1 mark question they can ask. So from numerical point of view, this slide is very important. Now atomic mass unit, AMU. The masses of atom, nuclei and the fundamental particles are expressed in unit called as atomic mass unit. And this atomic mass unit is defined as, very important, 1/12 part of mass of one of carbon atom. It's very important. It is the 1/12 part of mass of carbon atom, and carbon atom is denoted by 12C6. So 1 AMU is equal to 1/12 into mass of carbon atom. From numerical point of view, this statement is important, and also from multiple choice question can also be made. 1/12 part of mass of carbon atom. Instead of carbon atom, they can give you another other atoms. So be careful. It is a 1/12 part of mass of one carbon atom. 1 AMU is equal to 1/12 into mass of carbon atom, as I already told you. So 1/12 into 12 divided by 6.0 into 10 to the power 23, which will be equal to 1.67 into 10 to the power minus 24 grams, or in terms of kg, it is 1.67 into 10 to the power minus 27 kg. From fill in the blanks point of view, they can ask 1 AMU is equal to dash. So either in terms of gram or in terms of kg, you should be thorough. If it is in grams, 1.67 into 10 to the power minus 24 grams. Or if they are asking in terms of kg, it will be equal to 1 AMU will be equal to 1.67 into 10 to the power minus 27 kg. It's very important. 1 AMU is equal to 1.67 into 10 to the power minus 27 kg. Now the next topic is packing fraction. So first, before that, the mass number A of a nucleus is an integer. Very important. Mass number A of the nucleus will always be equal, is an integer, whereas the actual mass capital M of the nucleus is not an integer, is never an integer, is not an integer. Based on this slide, they can ask you true or false. There is a possibility of fill in the blanks as well as true or false. So mass number of A of nucleus is always integer, whereas actual mass M of the nucleus is not an integer. R.T.M.N.U is the name of the scientist. In order to express the deviation of actual mass from the atomic mass number, actual mass is denoted by capital M and atomic mass number is denoted by capital A. In 1927, R.T.M.N.U defined the difference in terms of packing fraction. So what is packing fraction? Packing fraction is defined as mass defect per nucleon in the nucleus. There is a possibility that they can ask true or false based on the statement mass defect per nucleons of the nucleus, or they can ask the mass defect per electron in the nucleus or mass defect. Likewise, they can construct in any way. So the correct answer is packing fraction is defined as mass defect per nucleon in the nucleus. If capital A is the atomic mass number, that is total number of protons and neutrons in the nucleus, and capital M is the actual mass of the nucleus, then packing fraction is given by, it is denoted by F is equal to del M upon capital A is equal to M minus A upon A. From numerical point of view, this slide is very important. They can give you the value of del M and A and they will ask you to find the packing fraction. Or from the from the fill in the blanks point of view also, this slide is very important. This figure gives packing fraction curve. On the x-axis it is the mass number A and on the y-axis it is packing fraction per nucleon. As you can see, as the atomic mass number goes on increasing, the packing fraction per nucleon goes on decreasing and it crosses the zero and it goes to the negative part, and slowly after Fe you can see there is a slight rise and it touches the zero at Hg at 180, and after that there will be increase in the curve. So it is a very important curve. They can give you the curve and they will ask you the name of the curve. So this is packing fraction curve you need to write, and this on the x-axis it is the mass number and on the y-axis it is the packing fraction per nucleon. So what are the conclusions drawn from packing fraction curve? As just now I in the last slide as we saw. So some of the important conclusions, and based on this upcoming slides, they can ask you fill in the blank question as well as true or false can be based on this slide. So first conclusion, for most of the nuclei, A greater than 20 and A less than 200, the packing fraction is negative. So in place of negative, for true or false, they can give you as a positive. So very important, for the most of the nuclei, A greater than 20 and A less than 200, the packing fraction is negative. For few light elements and heavy nuclei, very important, we are speaking about light elements and heavy nuclei, that is A less than 20 and A greater than 200, the packing fraction is positive. Remember this, they can ask either as a true or false or for multiple choice question. For all nuclei from A greater than 60 to A less than 160, the packing fraction is nearly proportional to mass number A. Very important. For the nuclei from A greater than 62, A less than 160, packing fraction is nearly proportional. Here it is directly proportional to the mass number A. More the mass defect in formation of the nucleus, more stable is the nucleus. So true or false based on this, as well as fill in the blanks based on this, can be asked in the exam. So it's very important. More the mass defect, the nucleus will be more stable, and vice versa. More negative the packing fraction of the nucleus will be more stable. If the packing fraction is more negative, then the nucleus will be more stable. Now we are going to see binding energy. There is some mass defect, as we already saw, A minus M, when nucleons combine to form nucleus. Actually, this loss of mass of nucleus is released in the form of energy during the formation of the nucleus. When the nucleus is being made, then during that formation period, the mass defect, the difference in the mass will be lost in the form of energy, and it is governed by famous Einstein mass energy relation, that is E is equal to, we know that E is equal to mc square, but in this case it is E is equal to delta mc square, where delta m is the mass defect. This energy is called as binding energy of the nucleus. Very important, this energy is called as binding energy. So numerical based on this can be asked, or true or false can also be asked based on the slide. So binding energy is defined as energy released in the formation of nucleus by combining the nucleons. When the nucleons get combined, during that time some energy is released. We know that that is the mass defect, and this is nothing but the binding energy of the nucleus. One more definition is there for binding energy, that is the external energy required to isolate the nucleons. If you want to isolate the nucleons, then you need to provide external energy, and that external energy is also called as the binding energy. So here the binding energy is termed for the two things. One is when energy is released, during that time it is called as binding energy. At the same time, when we provide energy to isolate the two nucleons, at that time the energy we provide, that is also called as the binding energy. So true or false can be asked based on the slide. Remember this formula, binding energy E suffix B is equal to delta M into C square. Numerical based on this formula can be asked. The binding energy of the nucleus with atomic number Z and mass number A E is given by EB, that is the binding energy, is denoted by E suffix B, is equal to Z times MP plus A minus Z times Mn minus M into C square, where C is the velocity of the light, capital M is the mass of the nucleus, MP, M suffix P is the mass of the proton, Mn is the mass of neutron. This formula is important from fill in the blanks point of view, as well as from the numerical point of view. They can give you the value of MP, Mn, Z and A, and M also. They will ask you to find the binding energy. Again, one more important formula, nuclear mass capital M is equal to Z times MP plus A minus Z times Mn minus EB, that is the binding energy, divided by C square. Again, this formula is very important from fill in the blanks point of view, as well as from the numerical point of view. Binding energy of the nucleus is equal to delta M into C square. Maybe they can ask numerical based on this. They will give you the value of delta M, that is the mass defect, and C you already know, C is equal to velocity of light is 3 into 10 to the power 8 meter per second. Very important. If they give you delta M in SI system, then use proper notation. If it is in CGS, use proper values of C, and accordingly the value final answer will get changed. So dear students, while solving the numericals, keep in mind the system should be in the system should follow one complete same unit international. If it is in SI system, then follow SI system, and if it is following CGS, so keep in mind the unit should be in CGS. Binding energy per nucleon is given by delta M del m into c square upon a, very important. We know that del m upon a is a packing fraction, it is denoted by f. So this equation can also be written in the form of f into c square. They can give you the packing fraction f and they will ask you to find out binding energy per nucleon. The numerical based on the slide can be asked, and this formula can also be written as binding energy per nucleon is equal to c square into packing fraction. Very important to note. Numericals they can ask. The average binding energy is defined as binding energy per nucleon. When we will divide binding energy by the nucleon, then we will get average binding energy, and it is denoted by E suffix B, that is binding energy divided by A. So EB upon A is equal to C square upon A into bracket Z times MP plus A minus Z times Mn minus M, and EB bar, that is the average binding energy, is also written as EB bar is equal to C square Mn minus Z upon A, Mn minus Mp minus M upon A. Numerical based on this can be asked. The binding energy per nucleon of the nucleus relate to the stability of the element. Here it means the stability of the nucleus, whether it is stable or not stable, can be found with the help of binding energy per nucleon. So true or false based on this can be asked. Very important. Average binding energy is maximum when packing fraction is minimum. Very important. True or false based on this can be asked. Average binding energy is maximum when packing fraction is minimum. Since the nuclei of mass number A, that is A is between 20 and 200, that is 20 is less than A is less than 200, the packing fraction is negative. Very important. When A is between 20 and 200, the packing fraction is negative. Hence, average binding energy will be more. Higher the binding energy per nucleon, more stable is the nuclei. It's very important. Whatever whatever words are appearing in the bold letters, they are very important from true or false point of view as well as from the fill in the blanks point of view. Since the nuclei, again I will repeat, A is between 20 and 200, the packing fraction is negative, means average binding energy will be more. Higher the binding energy per nucleon, that is the average binding energy, if it is more, then more stable is the nuclei. This is the binding energy curve. It is plotted between nucleon number A on the x-axis and binding energy per nucleon, that is in mega electron volt, capital MeV, on the y-axis. Very important. Nucleon number A on the x-axis and binding energy per nucleon on the y-axis. And the binding energy per nucleon is having the unit mega electron volt. The lighter nuclei, the binding energy per nucleon changes very irregularly from one nuclei to other nuclei. So when we move in the periodic table, there is irregularity is observed for the light nuclei elements. Other than nuclei, we are speaking some nuclei, but we are discarding the nuclei such as 4He, 8Be, 12C, 16O and 20Ne. The binding energy curve for all other nuclei is continuous and almost linear. For all nuclei except for 4He, 8Be, 12C, 16O and 20Ne, other is continuous and linear when you observe the binding energy curve. But this is not true for, again I am repeating the same element name, that is 4He, 8Be, 12C, 16O and 20Ne, because they can ask fill in the blanks based on these elements. This is helium, beryllium, carbon, oxygen and neon. Other than this nuclei, all other nuclei shows continuous and linear graph. The binding energy per nucleon of some light element, again remember the light nuclei such as 1H, 2H and 3He is very low, but for all other nuclei it is nearly equal to 8 mega electron volt. Fill in the blank question they can ask. What is the binding energy per nucleon other than these elements? It is 8 mega electron volt. We've seen that higher the binding energy per nucleon of the nucleus, the more stable will be the nucleus. Nuclei with number of neutrons or protons equal to 2, 8, 20, 28, 50, 82, 120. Remember this number. The number of neutrons or protons is equal to such number, then it will be more stable compared to the neighboring elements. Hence, when we just now in the previous slide, we just talked about 4He, 8B, 12C, 16O and 20Ne. They belongs to this category, and this number 2, 8, 20, 28, 50, 82, 120 are called as magic numbers, and if the number of neutrons or protons of a nuclei is equal to this number, then it will be relatively more stable. So true or false based on this can be asked. Nuclear reaction, now we are going to see. Nuclear reaction is the process in which on bombarding an energetic particle, we are going to bombard a nucleus, a target nuclei with energetic particles such as it can be neutron, proton, deuteron, alpha particle or gamma photon. When we will bombard a target particle with this particle, energetic particle, then another particle is emitted and the nucleus changes into a nucleus of some other element. Suppose a particle A is bombarded on a nucleus of X, it changes into nucleus of Y, and particle B and particle with the liberation of particle B. This nuclear reaction is expressed as follows: A plus capital X will give you capital Y plus B plus Q, where Q is the energy emitted or absorbed in the nuclear reaction. In a nuclear reaction to take place, either the energy will be emitted or it will be absorbed. So absorbed, that is, it is indicated by letter Q. Again, this slide is very important. If the value of Q is positive, it means energy is emitted. If Q is positive, energy is emitted in a nuclear reaction. And if the value of Q is negative, the energy is absorbed in a nuclear reaction. Very important, these two terms. When Q is positive, energy is emitted. When Q is negative, energy is absorbed. Now I will not go into much into the details of the derivation. I am just taking because since your exam is in the form of MCQ. So I will directly take the final result. Q is equal to mx plus ma minus my plus mb times c square, where mx is the mass of nucleus capital X, ma is the mass of projectile A. It can be neutron, it can be proton, deuteron or alpha particle or gamma photon. My is the product nucleus and small mb is the emergent particle. And c is velocity of light, that is 3 into 10 to the power 8 meter per second. If mx plus ma is greater than my plus mb, then Q value is positive and the reaction is exothermic or exorgic, that is, energy is released in the reaction. You need to remember this from true or false point of view. If mx plus ma is less than my plus mb, then the value of Q is negative and the reaction is endothermic or endorgic, that is, energy is absorbed in the nuclear reaction. If mx plus ma is equal to my plus mb, then Q value, here there is no Q, means Q is equal to 0. In that case, the reaction will be elastic collision will be takes place. Elastic collision, this is a condition for elastic collision, that is Q is equal to 0, and then in that case mx plus ma is equal to my plus mb. In 1930, both and Baker bombarded beryllium with alpha particle and found that a very penetrating radiation was produced. and this radiation was very high in energy, and hence he termed as gamma radiation. According to the nuclear reaction, you remember this nuclear reaction from fill in the blanks point of view. 4Be9 plus 2He4 will give you 6C13 with the liberation of H.N.U, that is the gamma radiation. Remember this number. The energy of gamma ray was found to be 7 mega electron volt. Remember the unit, it is mega electron volt, and it is equal to 7 MeV. Thus, it was deliberated that neutron is one of the fundamental particles constituting the nuclei of the atom. And some of the characteristics of a neutron is it is neutral particle having mass 1.00898 AMU, that is atomic mass unit, and it is nearly equal to that of proton, and it is having spin half, hence it is a spin half particle, and it obeys Fermi-Dirac statistics. Very important, it follows Fermi-Dirac statistics. We are going to see nuclear fission process. Here you can see from the diagram, a slow neutron is approaching towards uranium 92, uranium 235 92, and when it gets bombarded, then after the reaction it will convert into barium and krypton with the liberation of 3 neutrons, and high amount of energy is liberated out. When uranium 235 92 is bombarded with slow neutron, that is 0 N1, it will give you another product nuclei, that is barium 141 56 plus krypton 92 36 with liberation of very important 3 neutrons, and neutron is given written as 1 and 0. And remember this formula, chemical reaction from fill in the blanks point of view. Nuclear fission. Nuclear fission is the process in which a heavy nucleus, here they used uranium 235, splitted into two light nuclei, as we saw barium and krypton, nearly of the same size, by bombarding it with neutrons. The process of fission was discovered by R.T.M.N.U and his two associates, Meitner and Strassman, in 1939. R.T.M.N.U and Strassman bombarded uranium-235 with thermal neutrons. It was observed that nucleus of uranium-235 split into at least two nuclei, barium and krypton. It can be other nuclei also, but in major it is barium and krypton with ejection of 3 neutrons. Very important, 3 neutrons are liberated out, and tremendous large amount of energy is evolved out. Going to see liquid drop model. The nucleus is supposed to be spherical in its stable state, just as liquid drop is spherical. Very important, it is spherical due to symmetrical force of surface tension. The most stable shape of nucleus having radius r is given by r equal to r naught a to the power 1 by 3, where capital R is the radius, and the nuclear density. Here I want to add something. The nuclear density is constant and is independent of nuclear size. You remember this, the nuclear density is constant and is independent of the nuclear size. The nuclear density is constant and is independent of the nuclear size. This is similar to the fact that density of the drop of the liquid is same and independent of their sizes. Next, the short range and saturation property of nuclear forces are analogous to cohesive force between the molecules in a liquid. The short range and saturation properties of nuclear forces, it is equal to the cohesive force between the molecules in a liquid. Latent heat of vaporization is constant for a liquid, and in the same manner the binding energy per nucleon is also constant. Based on this, fill in the blanks for true or false can be asked. The formation of compound nucleus during nuclear reaction is similar to condensation of vapors of a liquid into a drop. And next point is different types of elementary particles are emitted from the nucleus. which is in analogous to emission of molecules during evaporation. We are familiar with the evaporation process. Whatever happens there in evaporation, in a similar manner, elementary particles are emitted out from the nucleus. This model does not attempt to describe the motion of each nucleon present in the nucleus. This liquid drop model does not explain the motion of nucleons present in the nucleus, whereas it concentrates on collective behavior due to coherence of all the nucleons. It just concentrated on the collective behavior of the nucleus. It successfully explained the phenomena of nuclear fission. A single neutron causing fission in a uranium nucleus produces three prompt neutrons. As we already saw, one neutron, when it is bombarded to uranium, it will give out product nuclei such as barium and krypton. Along with that, it gives three neutrons. These three neutrons which is produced will again go and again it will bombard to another 3 uranium and giving out 9 more neutrons, and the condition and this process will continue. This process happen in the chain reaction. It is not stop there, and it will go on bombarding another uranium, and with the liberation of again 3 neutrons, it will again bombard another 3, and it will go on. A single neutron cause fission in a uranium nucleus produces three prompt neutrons. If the three prompt neutrons produced in the reaction disintegrate, three more uranium-235 nuclei, giving 9 more neutrons, which in turn produce fission of the 992 uranium-235 nucleon, and so on. Thus, a chain reaction would start, and a tremendous amount of energy will be liberated in a very short time. As in the figure, you can see easily a slow neutron which is bombarded on the uranium-235-92. It gives out barium and krypton with the ejection of three neutrons. Three neutrons again bombarded to the another 3 uranium, and as a result 9 neutrons are given out. Remember, in this 3 neutrons are given out. Maybe they can ask to fill in the blanks based on this. There are two types of chain reaction. One is uncontrolled chain reaction and another is controlled chain reaction. The uncontrolled chain reaction will go faster and faster as it is self-accelerating. And as we already saw, one neutron will liberate after bombarding to uranium-235, it gives 3, and again it will again bombarded on the 3 without any external supply of energy, and it is a self-accelerating type reaction, self-accelerating, and ultimately the entire substance gets fissioned in a very short duration. A tremendous amount of energy is released, which takes the form of a big explosion, as we already saw in our history. Hiroshima and Nagasaki is the best example of this reaction. This happened as in atom bomb. Very important. A tremendous amount of energy is released. Controlled chain reaction. The fission reaction is so controlled with the help of controllers. Some type of controllers are provided and moderator, such that out of the few neutrons obtained in a fission, each fission reaction, only one neutron is able to fission the other new nuclei. Thus the rate of fission becomes very slow and steady. The energy obtained in it is used for the constructive purposes. Nuclear reactor is the best based on this principle. As we saw, a slow neutron is bombarded on uranium-235. It gives out barium and krypton as the product nuclei, bigger nuclei of similar size, nearly of similar size, with the liberation of 3 more neutrons. These 3 more neutrons, out of these 3 neutrons, the 2 neutrons are disabled by the use of controllers and moderator, and only one is allowed to carry on its further reaction. So it can be controlled. The reaction is very slow and steady, and this is used in nuclear reactors. In the generation of electricity also, this type of technology is used. So in order to control the chain reaction, they are making use of controllers and moderators. Then we should know what is controllers, what are the moderator. In the upcoming slides you can see. So based on this, they can ask what ultimately control the chain reaction. So it is the controllers and the moderator. Out of 3 neutrons, only 1 neutron is allowed to carry out the reaction, and the other 2 neutrons are suppressed. Reactor is a device in which a controlled nuclear chain reaction can be initiated and sustained to produce energy for the constructive purpose such as generation of electricity. We all are aware of all these things. So nuclear reactor, with the help of this energy generated, we can use for the constructive purpose. India has about 21 nuclear reactors in operation in 8 nuclear power plants, and it is having capacity around 5780 megawatt and producing a total 30,000 gigawatt of electricity. And some of the nuclear reactors are Apsara, Dhruva, Purnima, etc. Nuclear reactors. In nuclear reactor, then the reaction takes place is chain reaction. Obviously, it is a controlled chain reaction. It is under the control. But before that, we should know what are the fuel used there. So fuel is a fissionable material like uranium-235-92, uranium-238-92, uranium-239-94. Remember this uranium numbers because they can ask in the fill in the blank. Then moderator, heavy water, graphite and beryllium oxide are used to slow down the fast moving neutrons. Because in the control chain reaction, when 3 neutrons are liberated out, we only need 1 neutron to proceed. So we need to first slow down the neutrons and later on they will suppress by the control rods. So moderators are heavy water, graphite and beryllium oxide. Remember this examples of moderator. Then tremendous amount of energy is heat is liberated out and it will affect the reactor. So coolant system is needed. For that case, cold water will be provided or liquid oxygen are used to remove the heat generated in the fission process. And the last is the control rods. Control rod, again remember, cadmium or boron rods are the good absorber of neutrons. If neutrons are liberated, then these two rods, that is the cadmium or boron, they will absorb and therefore can be used to control the fission reaction. If in order to control the fission reaction, we can make use of cadmium or boron rod, it will absorb the neutron and thus the reaction can be controlled. Nuclear fusion. Nuclear fusion is a process in which two light nuclei combine to form a heavy nucleus. In fusion, huge amount of energy is released. In fact, when two light nuclei combine, the mass of the product is less than the sum of the mass of the two combining nucleus, as we already discussed in the first few slides. But remember this reaction, 2H1, that is deuteron plus 2H1 deuteron will give you 3He2 plus that is helium isotope plus liberation of 1 neutron, 1N0 plus 3.3 mega electron of energy. Remember this reaction because they can ask the reaction in the exam. 3He2, that is helium isotope, then again will bombard on 2H1 deuteron, it will give you 4He2 helium which is stable plus liberation of 1H1, that is a proton, plus 18.3 mega electron volt of energy. These above two equations are very important. Thus, in all, 3 deuteron nuclei fuse to form a new helium nucleus with a release of 21.6 mega electron volt energy. The process of nuclear fusion is not possible at ordinary temperature and pressure. Remember this temperature and pressure. It needs high temperature and high pressure, and high temperature is of about 10 to the power 7 Kelvin and high pressure is of about 10 to the power 6 atmosphere. This it happens in hydrogen bomb, and also this reaction used to happen in the sun. Energy from the sun is based on the fusion process. This 21.6 mega electron volt, remember this number from fill in the blanks point of view. Let us see the shell model of the nucleus. The shell model of the nucleus was proposed in 1950 by Maria Mayer, Jensen and Wigner. These are the name of the three scientists. Remember these names from MCQ point of view. In the shell model, nucleons are assumed to move independent of each other in an average centrally symmetric potential, taking the Pauli's exclusion principle into account. Here they follow the Pauli's exclusion principle. The same kind of effect is observed when with respect to nuclei. When nuclei is having, as I already told you, 2, 8, 20, 28, 50, 82 and 126 neutron number or protons, then that nuclei is more stable compared to the neighboring elements, other nuclei with the similar mass number. These numbers are called as, I told you, remember this, these are called as magic numbers. And using this analogy, a series of protons and neutrons placed in a certain discrete levels or shells, just like electrons in a shell of an atom, and hence the name is given shell models of the nucleus. Just quickly revise what is Pauli's exclusion principle. According to Pauli's exclusion principle, two protons with opposite spin and two neutrons having opposite spin are accommodated in a particular shell. Very important. From true or false point, this line is very important because we already know the either 0 or 1, and this is another definition for that. Two protons with opposite spin and two neutrons with having opposite spins are accommodated in a particular shell. In this way, first shell accommodates two protons and two neutrons and is more tightly bound than other shells. Remember, according to Pauli's exclusion principle, either 0 or 1, possibility of 0 or 1 is there. In the similar manner, if here we are talking about the protons and neutrons, then protons with opposite spin and two neutrons with opposite spin, very important, opposite spin is very important, they can accommodate in a particular shell. So first shell accommodates two protons and two neutrons and is more tightly bound than other shell. Thank you.